There's a bridge in southern China that sits higher above the ground than the clouds themselves, hanging 565 meters above a river far below, taller than the Eiffel Tower, so high that commercial airplanes have genuinely been photographed flying underneath it, and driving across it feels less like crossing a road and more like floating through open sky with absolutely nothing solid beneath you at all. This is the story of how engineers built that bridge directly across a gorge that had been declared, formally and repeatedly, impossible to cross for more than a decade. Before this bridge existed, making that same crossing meant 5 brutal, punishing hours winding along mountain roads, a journey that most people living in the region simply accepted as an unavoidable fact of geography. Because the alternative, building a bridge across a gorge this extreme, had been attempted, studied, and abandoned so many times that engineers had essentially declared it impossible. Guizhou province, tucked into the mountainous interior of southern China, has always been one of the most physically isolated regions on the entire planet, home to millions of people who lived almost completely cut off from the rest of the country, with no meaningful highways, no fast routes in or out, nothing resembling modern transportation infrastructure connecting them to the wider Chinese economy. In fact, Guizhou didn't have a single expressway of any kind until the year 2000, an almost unbelievable fact for a province home to millions of residents at the dawn of the 21st century. Eventually, China's central government made a bold, deliberate decision. Connect Guizhou to the rest of the country, no matter the engineering cost, no matter how many previous attempts had already failed. But there was one specific obstacle standing directly in the way of that ambition, a single monstrous gorge that had personally stopped every serious highway. Proposal in the region for 13 consecutive years. You might reasonably ask why engineers simply didn't build a conventional bridge across it, and the honest answer is that they tried repeatedly. And every single traditional bridge design that reached the drawing board ultimately failed under the sheer extremity of the site's conditions. The gorge itself was simply too deep, too wide, and too exposed to brutal mountain winds for any standard engineering approach to reasonably survive. Before anyone could even begin sketching a viable design, engineers spent a full 2 years exclusively studying the gorge itself, gathering data, before committing to any specific approach. And the wind measurements they collected during that study period turned out to be genuinely terrifying, with sustained gusts reaching up to 140 kilometers per hour, ripping through the canyon at irregular intervals. Finally, in 2011, one particular engineer proposed a design concept that would ultimately prove capable of actually solving the problem. A cable-stayed bridge anchored by towers built directly onto narrow cliff ledges rather than conventional flat ground, an approach specifically engineered around the extreme, unforgiving geometry of this exact location. Construction officially began in November of 2011, and the challenges started essentially immediately. Every single anchor point required for the foundation had to be drilled entirely by hand directly into solid rock, because the site was so cramped and so extreme that standard construction machinery simply could not physically fit into the available space. The entire location was so remote and inaccessible that even ordinary construction cranes couldn't function properly, forcing engineers to design an entirely custom cross-gorge cable system purely to move equipment and materials back and forth across the open gap before real construction could even begin in earnest. Before any permanent structure could rise, a temporary access road first had to be carved directly into the cliff face itself, a process that ultimately required 200 separate controlled explosions to clear away enough rock, every single blast precisely calculated in advance to avoid destabilizing the surrounding cliff. After each individual blast, geologists carefully inspected every millimeter of the newly exposed rock surface, checking for hidden weaknesses that could threaten the stability of the entire foundation later in the project. 2 completely separate construction teams worked from opposite sides of the gorge simultaneously, racing independently toward a shared goal neither team could fully see from their own side. Each foundation anchor point ultimately had to be drilled 15 meters deep into solid bedrock, with absolutely no exceptions permitted anywhere along the entire foundation footprint, regardless of how difficult or time-consuming any individual drilling location proved to be. After 8 genuinely brutal months of continuous excavation and preparation work, both foundation pits were finally ready to receive their first pours of concrete. The concrete pour required for each individual tower foundation demanded 15,000 cubic meters poured in a single continuous operation, because stopping midway through a pour of that scale would have introduced exactly the kind of structural weak point that could eventually cause the entire foundation to fail under load. Buried inside all that concrete sits a steel reinforcement skeleton so dense that workers could barely walk through the open. Framework before the concrete was actually poured around it. Each tower then had to grow directly upward from the narrow edge of the cliff itself, rather than from flat, level ground, an entirely different structural challenge compared to virtually any conventional bridge tower construction anywhere else in the world. To manage that unusual growth pattern, engineers used a self-climbing concrete formwork system, a mechanized structure capable of rising a consistent 4 meters every single day as each new section of tower cured beneath it. Every single worker platform positioned at height throughout construction was fully enclosed, a critical safety measure given that the powerful winds, regularly sweeping through the gorge, could genuinely throw an unprotected worker clean off the structure without warning. Simply looking straight up at one of these towers mid-construction was enough to trigger instant vertigo in most visitors, even before the structure was anywhere close to finished. Tower 1 reached a full 100 meters in height in just 62 days, a pace that broke construction speed records even as the team continued building. Every single meter of vertical growth required a fresh laser alignment check, because being even a single degree off true, vertical anywhere along the tower's height would have required scrapping and rebuilding that entire section rather than risk long-term structural instability. While Tower 1 continued its steady climb, the construction team working on the opposite side of the gorge had already pulled roughly 40 meters ahead in height, an ongoing, informal competition that quietly pushed both crews to maintain relentless pace throughout construction. Winter arrived hard in 2012, with temperatures dropping well below freezing across the entire site. Yet work never fully stopped, despite the brutal conditions, crews adapting their methods and schedules rather than allowing the harsh mountain climate to halt progress entirely. Inside each completed tower sits an intricate system of pre-stressed cables specifically engineered to hold the surrounding concrete permanently under compression, adding significant structural resilience against the extreme forces the towers would eventually need to withstand. Every single computer simulation run against the finished tower design produced the same reassuring conclusion. This particular design could reliably handle essentially anything nature might eventually throw at it across the structure's entire operational lifetime. Eventually, the tops of both towers reached the exact same elevation as the surrounding gorge rim itself, and the final tower cap on each side had to be placed within just 5 millimeters of its precisely calculated target position. An extraordinary tolerance given the sheer scale and height already involved. Both towers were fully completed within 18 months of construction beginning, together representing 392 meters of solid concrete rising directly out of opposing cliff edges on either side of the gorge. Each completed tower top ultimately contains 56 separate cable anchor points, specifically engineered to reliably handle up to 4,000 tons of combined tension force once the full cable system was eventually installed. And yet, after 18 full months of construction and 2 completely finished towers standing on opposite sides of the gorge, the space between them remained entirely dramatically empty. The cable installation phase that followed turned out to be, without question, the single most technically demanding part of the entire project. Each tower ultimately required 56 individual cables to properly carry the full weight of the deck directly down to the foundations below, and each of those cables itself contained 109 individual steel wires twisted together under extremely precise tension specifications to form a single unified structural cable. To even begin the process, engineers used a helicopter to fly the very first thin pilot wire across the full 720-meter gap separating the two towers, with the pilot forced to hold a stable hover in crosswinds reaching 80 kilometers per hour while ground crews carefully attached the initial cable connections. A genuine feat of aviation skill under extraordinarily difficult conditions. Every single new cable added to the system inevitably altered the tension distribution across every other cable already installed, transforming the entire installation process into something closer to tuning an enormous, gorge-spanning musical instrument than conventional construction work. Each individual cable ultimately had to be tensioned to within 1% of its precise target load, a level of precision that left almost no room for error across dozens of interconnected cables. As each new cable was progressively tightened into place, the cumulative tension literally began pulling the not yet built deck sections into their correct final alignment even before deck construction had properly begun. After 28 cables had been installed on each side of the structure, the entire bridge began visually resembling something like the strings of an enormous sky-spanning harp suspended between two cliff faces. But then an unexpected problem emerged. The cables themselves began singing audibly in the wind, a phenomenon that also produced genuinely dangerous structural vibrations that engineers needed to solve quickly before the issue could compromise the cable's long-term integrity. Left unaddressed, that kind of uncontrolled vibration could eventually fatigue steel cable to the point of catastrophic failure over time. The elegant solution engineers eventually settled on involved installing viscous dampers, essentially giant mechanical shock absorbers, directly inside the housing of every single cable across the entire structure. Direct before and after comparisons under identical wind conditions confirmed that the dampers completely eliminated the dangerous vibration problem across all 56 cables on Tower 1 alone, everyone properly tensioned, dampened, and precisely aligned in what genuinely amounted to a form of pure structural engineering artistry. Every single cable was inspected centimeter by centimeter before construction was permitted to move forward into its next phase, ultimately resulting in 112 total cables stretching dramatically across the Beipanjiang River Gorge, forming what many engineers consider one of the most visually stunning structural achievements anywhere in the world. When the very final cable finally clicked securely into place, grown engineers who had spent years of their lives on this project were reportedly seen hugging each other openly and crying with relief and pride. Installing all 112 cables ultimately required 4 full months of continuous, painstaking work, each individual cable functioning as a literal lifeline connecting human ambition directly to solid bedrock hundreds of meters below. With the cable system finally complete, the actual bridge deck had to be built simultaneously outward from both towers at once, because building it unevenly from just one side risked tipping the entire partially completed structure. Each prefabricated deck section was manufactured entirely off-site, then flown into position using some of the largest construction cranes ever built anywhere in the world. Every single structural bolt used throughout deck assembly was torqued to an exact specification, then independently checked twice by separate inspection teams before being considered complete. Much of the required welding work had to be performed 565 meters above the ground, with workers relying on nothing more than a relatively thin safety net positioned far below them for protection. Every additional meter the deck extended outward from either tower required engineers to completely recalculate the structure's stress distribution from scratch, since each incremental addition meaningfully changed the overall load characteristics of the still incomplete span. Inside the completed deck sits a fully sealed steel box structure, with inspectors regularly required to physically crawl through its interior, checking every single weld along the way for any sign of defect. On some particularly brutal days, wind speeds at the site reached 120 kilometers per hour, yet construction work stopped for nothing, crews continuing to push forward despite conditions that would have halted most conventional construction projects entirely. Both halves of the deck continued, extending simultaneously from their respective towers, and the steadily narrowing gap between them gradually became the central countdown that the entire project team watched with mounting anticipation. When engineers finally measured the remaining gap, as both deck arms approached their final connection point, they discovered the two ends were misaligned by 3 full centimeters, a seemingly small but structurally significant discrepancy that needed correcting before final closure could proceed. By carefully adjusting tension across just 12 specific cables, engineers were able to gradually shift the entire deck structure back into proper alignment. After 18 continuous hours of extremely fine micro adjustments, the 2 deck ends were finally aligned to within just 2 millimeters of each other, an extraordinary level of precision achieved across a structure spanning well over a kilometer of open gorge. The final closing piece of deck, weighing a full 120 tons, had to drop perfectly into a precisely shaped gap of exactly the same 120-ton capacity, and when that closing piece finally landed successfully into position, the 2 previously separate sides of the gorge became physically joined together as a single continuous structure for the very first time in recorded history. Every bolt installation team involved in that final closure was carefully synchronized entirely by radio communication, with roughly 200 separate workers all moving in perfect coordination at the exact same critical moment. Workers on site began informally referring to that particular day as the moment the gorge itself effectively disappeared forever, replaced permanently by a continuous physical connection where none had ever existed before. In total, 1,341 meters of completed steel deck were finished across just 10 months of dedicated construction work, definitively marking the moment the gorge had finally, fully been overcome. Before any road surface could actually be applied, engineers first laid down a 20-centimeter reinforced concrete base layer across the entire completed deck. Paving the finished bridge surface itself took just 6 days of continuous work, crews operating around the clock without stopping until the entire surface was fully complete. Every essential safety system was installed simultaneously alongside that paving work, including crash barriers, lighting fixtures, lane markings, and directional signage across the entire length of the structure. Specially engineered expansion joints built into the deck allow the entire bridge to physically move up to 60 centimeters in response to temperature changes, because large steel structures like this one genuinely expand and contract meaningfully with shifting weather conditions. In Guizhou's particular climate, traffic, for the very first time, The very first official vehicle convoy completed the entire crossing in just 4 minutes, compared to the roughly 5 hours the old mountain route had always required for the identical journey. Elderly villagers, who had walked those same difficult mountain paths for their entire lives, were reportedly moved to tears witnessing the completed bridge for the first time, hardly able to believe something like this could ever actually exist connecting their remote community to the wider world. On opening day alone, more than 3,000 vehicles crossed the newly completed world's highest bridge, and within just 24 hours, images and footage of the finished structure had already been viewed by more than 500 million people online across the entire planet. For at least one local business owner, the completed bridge ultimately reduced delivery times by a remarkable 97% compared to the old mountain route, a transformation that went well beyond simple convenience and genuinely reshaped what commerce and daily life could look like throughout the surrounding region. Guinness World Records subsequently confirmed the achievement officially, recognizing the Beipanjiang Bridge as the world's highest bridge at 565 meters above the river below, a permanent entry into engineering history. For 13 years, engineers had repeatedly declared this exact crossing structurally impossible, and yet, given enough time, enough persistence, and enough willingness to solve problems nobody had ever solved before, they ultimately built it anyway. Step back from the individual construction milestones for a moment and think about what it genuinely means for a region to go from having 0 expressways at the start of the 21st century to hosting the tallest bridge on the entire planet within roughly a decade and a half. A transformation that compresses what took most developed economies the better part of a century into a single generation of relentless, deliberate engineering ambition. For the millions of people living throughout Guizhou province, before this bridge existed, isolation wasn't an abstract inconvenience discussed in economic reports. It was the defining fact of daily life, shaping which hospitals a family could realistically reach in an emergency, which markets a farmer could feasibly sell produce in, which schools and universities felt like genuine possibilities rather than distant fantasies separated by an entire day of mountain travel. A 5-hour journey across brutal mountain roads doesn't just cost time, it fundamentally limits the size of the world available to anyone living on the wrong side of that gorge, quietly capping ambition, opportunity, and economic mobility for generation after generation without anyone ever needing to make an explicit decision to hold people back. That is ultimately the deeper story sitting underneath every individual engineering statistic in this project. The concrete poured, the cables tensioned, the helicopter threading wire across open air in 80-kilometer-per-hour crosswinds. None of that technical achievement exists purely for its own sake, or purely to claim a Guinness World Record, however genuinely remarkable that record happens to be. It exists because a 4-minute crossing instead of a 5-hour one doesn't just save time. It rewires the entire economic geography of an isolated region overnight, turning villages that once existed at the practical edge of the map into places genuinely, meaningfully connected to hospitals, universities, markets, and opportunities that had previously felt like they belonged to an entirely different world. Consider, too, the sheer audacity required to spend 13 years accepting that a project was impossible, only to eventually reverse that conclusion entirely and build a 5-year, 3,500 worker megastructure, directly across the exact same gorge that had defeated every previous attempt. Engineering failure, in this specific context, wasn't actually a dead end at all. It was simply data, information steadily accumulating year after year about wind patterns, rock stability, and structural limitations, until eventually enough understanding had built up to make an entirely new approach, a cable-stayed design anchored directly into narrow cliff ledges, not just theoretically possible, but genuinely, reliably buildable. The 13-year gap between recognizing the problem and finally solving it represents an entire engineering culture patiently refusing to accept a permanent no, choosing instead to treat repeated failure as an evolving, ongoing education rather than a final verdict on what human beings were capable of achieving in this particular corner of the world. And there is something worth sitting with in the fact that every single one of the 3,500 workers who built this bridge was personally given the opportunity to walk across it before opening day, a detail easy to skip past quickly but genuinely meaningful in its own right. These were the exact people who drilled 15 meters into solid bedrock by hand, who welded steel 565 meters above open air with nothing beneath them but a thin safety net, who worked straight through freezing winter conditions in 2012 because the project's timeline simply couldn't afford to pause for the season. Giving every one of them a personal, ceremonial walk across the finished structure before regular traffic ever crossed it wasn't merely a nice gesture, it was a genuine acknowledgement that this bridge existed specifically because of thousands of individual human beings choosing, day after day, for 5 consecutive years, to keep showing up to an extraordinarily dangerous job perched on the edge of one of the most extreme construction sites on the planet. Today, the Beipanjiang Bridge stands not simply as a record-breaking structure suspended impressively above a river gorge, but as tangible, permanent proof of something considerably larger. That isolation, however deeply entrenched by geography or however many years of accumulated failed attempts precede a solution, is never actually a truly permanent condition, given sufficient engineering will, sufficient patience, and sufficient willingness to keep trying long after. Conventional wisdom has already declared the entire effort impossible. There's also a quieter, more technical lesson embedded inside this project that engineers studying cable-stayed structures on extreme terrain continue referencing years after the ribbon cutting, and it centers specifically on that moment when the cables began singing dangerously in the wind partway through installation. In almost any other high-stakes construction environment, a newly discovered structural vibration problem of that magnitude, emerging mid-project on a structure already representing years of accumulated investment, could easily trigger months of redesign, months of paused work, months of second-guessing an entire engineering approach that had already been publicly committed to. Instead, the response here was fast, targeted, and remarkably specific. Identify the exact mechanism causing the vibration, design viscous dampers precisely engineered to counteract that specific frequency, install them directly inside the existing cable housings without requiring any broader structural redesign, and verify the fix immediately through direct before and after wind testing. That kind of rapid, surgical problem solving under genuine pressure, with a fixed opening date already publicly announced and thousands of workers depending on continued progress, represents exactly the kind of engineering culture that separates projects which merely get finished from projects that get finished safely, on schedule, and to a standard capable of surviving inspection reports running 4,000 pages deep. It's worth remembering, too, that the entire cable installation phase relied on threading wire across 720 meters of open gorge, using a helicopter hovering in crosswinds reaching 80 kilometers per hour, a task that, described plainly, sounds almost recklessly dangerous, and yet was executed with enough precision and control that it became simply one methodical, carefully planned step within a much larger sequence, rather than the kind of dramatic, headline-grabbing risk it might appear to be in isolation. That's ultimately the quiet signature running through this entire project, from its earliest cliffside blasting to its final 4,000-page inspection report. Genuine extremity treated not as an excuse for improvisation, but as a reason for even greater precision, checked twice, tensioned to within 1%, aligned within millimeters, verified against computer models that ultimately proved, again and again, to be correct. 13 years of declared impossibility. 5 years of continuous construction. 3,500 workers, 112 cables threaded across open sky. One bridge, standing higher than the clouds themselves, connecting a region that had waited generations for exactly this kind of connection to finally permanently exist.